Hello everyone, my name is Cheryl and I'm very honored to have the opportunity to share my research that I conducted through the RISC Summer 2026 program on semantic safety filtering with natural language explanations. Let's begin by considering the following scenario. Imagine you are driving down a highway with the company of a robot assistant. On a particularly busy day, you might have trouble identifying every significant event that occurs in your environment. In a shared control setting, the robot's task is to detect these events and propose any minimally invasive correction to your current action that will keep you safe. For example, let's say a vehicle approaches from behind. From the vehicle's physical dynamics such as speed, position, and orientation, the robot believes it to be any ordinary car and smoothly intervenes to help you keep driving forward. However, a more semantically informed approach to processing the world may recognize that the bright red paint and flashing lights identify this vehicle as a fire truck on its way to handle an emergency. While continuing to drive forward in your current lane is physically safe, a more appropriate behavior in this scenario would be to slow down and pull over to allow the fire truck to pass through. To this end, we highlight a challenge with goal alignment and classical safety filtering when choosing safe alternatives. Ideally, when tasked with enhancing the performance of goal-directed humans by keeping them safe, a robot should be able to enforce physical safety constraints while also respecting the underlying goal or intent that directs this behavior. Existing safety filters, such as control barrier functions, will often find corrective actions by staying close in the physical action space while enforcing safety constraints. However, this optimization assumes that the immediate nominal action is indicative of the controller's broader goals and ignores crucial information about scene semantics and long-term goals that might inform the most appropriate behavior. The objective of our research is to endow robots with the ability to propose safe alternatives whose outcomes align with the nominal controller's goals semantically while justifying these corrections in real time. We propose semantic outcome-focused filtering with language explanations, a framework that extends physical task representations from classical safety filters to incorporate a semantic understanding of the human's goal. Specifically, our key insight poses goal alignment as an optimization problem in language space rather than action space to propose semantically informed, outcome-aware action corrections. In doing so, we allow the filter to reason about both the physical hazards and semantic goals in the task and produce natural language descriptions that clearly communicate why the filter makes each correction. Taking a closer look at this framework, we first learn a safety value function offline through reachability analysis according to a static constraint set that defines the physical hazards in the environment. We use this value function to define the forward invariance condition of the control barrier function. During the online filtering step, we sample multiple candidate control sequences that satisfy the forward invariance condition to guarantee physical safety. In order to verify the forward invariance condition across multiple steps in the future, we use a world model to predict each outcome in the trajectory. After projecting immediate next step actions over multiple steps into the future, we decode these trajectories into a language space using a VLM that describes the behavior or outcome in each trajectory. Finally, we identify the safe control sequence whose narrated outcome is the most semantically similar to the nominal narration simulated outcome, while simultaneously satisfying alignment with the human's overall task goal. In our experiments, we evaluate the VLM's performance as a language space decoder and semantic distance optimizer over 3 open-source models and a closed-source model. To isolate our results to purely account for each VLM's capabilities, we assume a perfect world model by using the known vehicle dynamics and simulation to compute the predicted outcomes t steps into the future. We find a strong correlation between the MCQA accuracy, or the proportion of filtering steps for which the semantic pipeline successfully identifies action that yields the most aligned outcome with the task goal, and the proportion of episodes for which the filtered nominal policy succeeds at reaching the task goal. In order to determine if the lapse in performance is a direct result of a poor semantic distance optimization or influenced by low-quality narrations, we qualitatively examine the outcome narrations alongside the justification for the optimization across models. Open-source models are prone to hallucinations when generating language descriptions for outcomes. In comparison, the closed-source model is the most effective at producing accurate narrations. However, after closer examination of the justifications produced after each semantic optimization, both open-source and closed-source models appear to perform well at identifying the most semantically similar outcomes and only fail in the pipeline as a result of the low-quality narrations. Next, we explore how filter performance changes as a function of the nominal policy's optimality. We simulate 6 possible goal-directed human controllers that each share the same goal, but vary with respect to how well they achieve this goal, decreasing in optimality over the x-axis. We find that as the nominal policy decreases in optimality, the traditional control barrier function has a harder time with aligning with the specified goal. By contrast, a semantic control barrier function that optimizes with respect to the goal description, regardless of nominal narration, demonstrates more robust performance. However, this performance is limited the more the optimization cares about the semantic outcome of the nominal policy in the short term. Our key takeaways are that semantic CBS find performant, safe alternatives that maintain strong alignment with the human specified task goal, but only if the narrations are high quality. Additionally, when we evaluate over a diverse set of simulated humans, the semantic CBF demonstrates more robust performance to decreases in human optimality, but only when using a far-sighted optimizer. Before concluding, I would like to take a moment to express my sincere gratitude to my mentors, Joe and Professor Baichi, for their invaluable support and guidance in developing this project. I'd also like to thank the wonderful members of the Intent Lab and the CMU RI community, as well as our generous funders who helped make this research possible. And of course, thank you so much for listening.